Welcome to video number 2 here of the first 2 sections of Unit 7. We were talking about approximating the area under the curve, or the accumulation here under the curve. We're talking about this amount, right? We're trying to figure out what exactly is this area that's trapped between the function and the x-axis. And we had said in the previous video that we can approximate by using some rectangles. And in this video, we're going to use that approximation to, and some additional information, because I have some information here that I didn't have before. I have the equation of this graph, at least from 0 to 2, it follows this equation pattern. So 0.5 t squared plus 1. What we're going to do is we're going to create some rectangles. Now, in the last video, I think I showed you that we could create 4 rectangles of varying heights, same base on the same bases, but varying heights. And if I add all these areas, it's going to be an underestimate of the actual retail price, right? So that's what we're going to do right now. So I'm going to zoom in, and I'm going to partition, I'm going to break up this interval from 0 to 2 into 4 rectangles. And if I do that, that means each rectangle is going to have a base of 1/2. This base will be 1/2. This base will be 1/2. This base will be 1/2. Now, I'm going to create what are called left-sided rectangles. They're called left-sided rectangles because I start at the initial x value and I go up until I hit the curve, and I'm going to use this height as the height of my first rectangle. And so I'm going to stretch it horizontally, and I'm going to draw it down. So this rectangle was built with a base of 1/2 and a height based off of the function value at 0. The next rectangle, I'm going to use the same base, 1/2, but this time the height is going to be whatever the height is at x equals 1/2, so the function value at 1/2, and then I'm going to scoot over straight across as best as I can and create that rectangle. The third rectangle is going to be, again, base 1/2, but the height is based off of the x-coordinate at 1, which would be the function value at 1, which would be this height. And then lastly, go all the way up until it hits it, and then I come down. So these should be the same 4 rectangles I drew in the previous video, and you can definitely see that their areas add up to less than the actual shaded part, right? But how do I find the area of these rectangles? Well, how do we find the area of any rectangle? We multiply base times height. So I'm going to say that this shaded region, or the total distance, can be approximated by, so I have to put the approximation symbol. So we're going to multiply base times height. So I know that the base is 1/2 in the first rectangle. And the height is based off of the function value at 0. So I'm going to say that times v sub q at 0, because that height, that function value, represents the height of the rectangle. And then I'm going to add that to 1/2 times vq at this x value, and this x value is 1/2, plus 1/2 times v of q of the next x value, which is 1, and then finally 1/2 vq at 1.5, or 1.5. That would be this one. So notice, even though I go all the way to 2, the function value, the y-coordinate at 2, doesn't get used because these were left-sided rectangles, and I have enough heights in order to create those rectangles. Now, eventually we'll do right-sided rectangles, and if we do right-sided rectangles, we start with the right side. We'll use this height and work backwards. But if I do that, and I'm just going to sketch this very, very lightly, if I do that, then these will represent rectangles that are overestimates to the actual area that I'm looking for. So I'm going to stick to my red ones here, these left-sided rectangles, and we'll go from there. Okay. So now I need to actually figure this out. Oh, but I have a formula. So I can use this formula to figure this out. 1/2 v of 0 means, what's the answer? The function value output that you get when your input is 0. So if I input 0 here, I believe I get 1 plus 1/2, and then I plug in 1/2. 1/2 squared, that's 1/4, times another half, that's 1/8, plus 1. So that's 1 1/8, plus, substitute 1 in here, so that's 1 times 1/2 plus 1, that's 1 1/2, plus 1/2 v cubed 1.5. 1.5 squared, that's 3/2, right? So 3/2 squared, that's 9/4, and half of that would be 9/8, plus 1. I believe, I'm trying to do this in my head, and I probably shouldn't. 9/8 plus 1, that's going to be 17/8. There. And then I add them all together, and I get an answer, right? Done. What I could do on my calculator, though, is if I have access to the calculator, and I'm not trying to do things in my head or on paper, I could say, hey, calculator, I should have turned it on earlier. I'm going to go ahead and type this formula into y1. And then I'm going to use the function notation on my calculator to give me the final answer. So as I get my calculator going here, let me clear some of the sigma. I'm going to go to y equals. Let's clear that out. And I'm going to type in the formula that was given. The formula which was 0.5 t squared plus 1. Well, I'm going to write it as 0.5 x squared plus 1. So the formula is saved. I'm going to go to the home screen. And I'm going to make the little fraction. Alpha x is one way you can make the little fraction. So I'm going to say 1/2 times the function that I saved in y1 evaluated at 0. So one way to do that is to do alpha trace and say, oh, look, y1 evaluated at 0. Plus another 1/2 times y1 at 0.5. Plus another 1/2. But I don't know if you noticed, all of these terms, because they had the same base, all of them have 1/2, 1/2, 1/2. So I'm going to factor that out, and then I'm going to be left with the function values that I need to do, and that might make my calculator button pushing a little bit nicer and quicker. So I'm going to go back and I'm going to insert, second delete, insert something that should be there. And now I only have 1/2, but inside the parentheses, I'm going to do alpha. I guess I'm not going to do alpha. I'm going to do alpha trace 1 at 0.5 plus alpha trace 1 at 1 plus alpha trace 1 at 1.5. And when I do this, whammo bammo, I get my sum, 2.875. So I'm using function notation using the calculator. I can only do that if I have an equation saved in one of the y's, y1, y2, y3. It doesn't matter where it is. But if I use function notation, meaning I am using the name of the equation, open parentheses, whatever value I want to substitute, close parentheses, this just found this for me, 2.875. Now, is this the actual retail price? No, this is an underestimate, right? We had said that perhaps we could use trapezoids to get an overestimate and then go from there. But I also want to say I could, now that I know that the equation for the curve, remember the equation for the curve here is 0.5 x squared plus 1. Now that I know that, I could make two trapezoids and maybe reduce that error even more. So now I can draw one trapezoid in yellow, another trapezoid in yellow, find those areas and combine them. How do we do that? Well, remember we said the formula for the trapezoid is base 1 plus base 2, average it, divided by 2, and then multiply it times the height. So if we're going to do the trapezoid approximation, the trapezoidal approximation is find base 1, well that's the y value, or in this case the function value at 0, plus the function value at 0.5 divided by 2 and multiplied by the height. The height is this one on the bottom, which is 1/2, plus this other trapezoid, which would be VQ of 0. Oh, I'm sorry, not 0.5. My mistake. The height that I'm measuring of the trapezoid is at 1. And then the next trapezoid would be the height of 1, the height at 1, plus the height at 2, all divided by 2, because I need to take the average of the bases, multiplied by 1/2. If I do this on my calculator and I put it together, I'm going to get my estimate. Now, I will point out something. Notice that I made more trapezoids, 2 of them, compared to this example where I only did 1 trapezoid, and you can tell that the error got minimized. And again, it's pointing to this idea that the more shapes I make, my error or my offness on my approximation goes to 0. And that's an idea that we're going to use over and over again. So I'm not going to find the approximation for the trapezoid, but if you want to put this in your calculator, and if you have the equation saved in y1 and you're using y1 notation, you can figure that out. The moral of the story is we're trying to find the area of a curved space, and that's not really possible with the formulas that we have. And so I guess key concept number 2 here is there's several ways to approximate area under the curve. In AP Calculus, we're going to use rectangles or trapezoids to approximate it. And so in the next video, as we use the Riemann sum approximation, we're going to figure out that rectangles that we're drawing are actually called Riemann sums. And we need to always ask ourselves 2 questions whenever we do the approximation with rectangles. How many rectangles are we going to use? Because we're going to need to split my interval into that many sub-intervals. That's going to be the base of the rectangle. And then which method am I going to use for the height? Am I going to use the left side and start from the left and move that way? Or am I going to start on the right side? I guess the camera's backwards. Right side and go that way, or left side and go this way? Or am I going to use midpoint? And that's what we'll be doing for the next class and a half, is kind of playing with those Riemann rectangles and approximations.